let's uh, let's maybe start here, and I can welcome you into the course. Hopefully, you've had a moment here just to take a look at what we're going to cover for today. And as you might imagine, we're going to naturally start with some introductions and some practical course information, so we can jump right into that stuff and maybe say a little bit about who we are. I suppose I trust at this point I've been using Zoom enough that everyone can hear me just fine. But my name is David Whipp, and I am one of the course instructors for this course, and then also the Introduction to Quantitative Geology course that some of you might have an interest in taking that follows in period number 2. And I've been teaching this course now for something like 6 or maybe even 7 years, and it's slowly been developing over that time into what it is now. But I'm one of the people who's been around for, well, basically the duration of the course. And the other lecturer or other main teacher for the course is Håvard. And maybe Håvard, do you want to just say hello for a second?
Yeah. Hi, everyone. So my name is Håvard Augustin, and I am a PhD student at the Digital Geography Lab. So I am new in this course, but will be teaching both here and the Automating GIS course that is following this one. Yeah.
All right. Yeah. Thanks, Håvard. And we have also 2 course assistants. I don't think I saw. I guess Brian is here in the Zoom, it looks like. So Brian, maybe you just want to say hi.
Sure. Hello, everybody. Nice to see you. Good morning. I would be happy to assist in this course. So I'm here to help you. If you have any questions, something related about the classes, I will support you. So please don't hesitate to talk to me. I will be happy to help you. Thanks, David.
Yes. Well, thank you, Brian. And our other course assistant is Aleksi Rantanen, who was a course assistant for the Geo-Python course last year as well. So I think we have a good amount of experience with our group. And Brian, maybe just to remind you to mute your mic, just in case you didn't want to have it unmuted. Thanks.
Thank you.
So yeah, that's who we are, and just some more practical information for you. We have some course web pages that are going to be quite useful for you. The one at the top is the one that will be relevant to this course, and that is the main course page for the Geo-Python course. And we will go there maybe in a little bit. We can take a visit to the Geo-Python course page, but you've probably seen it in the email if you received the email about the course earlier when we sent out the basic information. But for those who are interested in the courses that follow, the second part of the AutoGIS course has its own webpage, and you can find a link here, as well as the Introduction to Quantitative Geology course that has its own website as well. And that course, if you go and visit there, you'll notice it's still the 2019 version of the course materials that are up, but you can have a look and still get some pretty decent sense of the kinds of things that are covered in that course. So these are certainly going to be handy for you. Particularly the link at the top is something that you will probably be visiting pretty much every week during this course, as that will be the place where we host all of the course materials. And in fact, maybe what I'll do is just take a quick look there now, because this is what the course page looks like if you haven't been there. And we have here all of our basic information about the course. You can go and, for instance, find the information about when we meet, who the instructors are for the course. So myself, and you'll find Håvard's name there as well as the course assistants, Brian and Aleksi, and other links to courses that might be useful to you. You can also find information there about the goals for the learning in the course and the things that are graded. This is probably something you'll want to pay some attention to because, of course, you're, I'm guessing, somewhat interested in the outcome from the course. So you can see here how the grades break down, and that we're basically getting 60% from the weekly course exercises and the 40% from a final course project. You'll also find for each week of the course the lesson materials over here on the left side, and we'll go there when we start into lesson 1 in just a few minutes. So you have that information, and I hope you'll find these course pages nice and easy to navigate. And if there's anything you find missing, please feel free to let us know. As noted already, you're here, so you probably have figured out that we're meeting at 9:15 on Wednesdays for the lessons. These are the online lessons that we'll have each week, and these are going to be, as noted, they'll be recorded, but it's great if you can be here. And there are sort of semi-interactive online lessons, so you may also find it's easier to be here and participate in these lessons than it is to watch the lecture video later. In addition, we have 2 work sessions, one on Thursday, one on Friday. Some of you may have enrolled to one or the other, or may have been automatically assigned to one or the other if you've used the SISU system at the University of Helsinki. I believe it will just put you in one or the other of the work sessions. There's a couple things to note. These are totally optional, so you don't need to attend them at all. They're basically there to support you in working on the course exercises. So one of the course assistants will be present at this time on either Thursday or Friday, and they can answer questions and give you some guidance on how to work on the course exercises. Essentially, it's like a practical session, but it's totally optional because you'll already have the assignment given to you through the course webpage. So if you're fine and comfortable to work on your own, then that's completely okay to do things that way. Now, an additional thing to consider this year is because the COVID restrictions are sort of slowly rolling back, we have access to a physical classroom for these work sessions. They are planned to be run in a hybrid fashion, so you'll be able to join online, or you can come and you can actually participate in the classroom for those sessions. And we've created a little spreadsheet. I think maybe we'll come back to the spreadsheet to show you how it works and what it looks like. But basically, we have a restriction on the number of people that can be in the classroom because of the COVID situation at the moment. The limitation is only 14 people, so we're going to have a system for people to sign up so that we don't end up with 50 people trying to come when there's only space for 14. So we'll come back to that, but basically the main thing to remember for right now is that these are optional. They will be run as hybrid sessions, so you can participate remotely if you prefer to do that. And if you want to come in person, we'll have a sign-up sheet for how to do that, or a spreadsheet basically for how to do that. Now, Hofard, I don't know if you have anything to say more about the AutoGIS, or just want to maybe remind people how things work with the 2 course codes.
Yeah, I can do that briefly. So the 2 courses, the course that you're in right now, Geo-Python and also GIS, or automating GIS processes, are connected. So for the first course, you get 5 credits, and then you can also get 5 more credits for the second course. So the Automating GIS course is intended for those who have taken this course and want to advance your knowledge in using spatial data with Python, making maps and doing spatial analysis. And the courses are built in kind of the same way. So if you enjoy this course and want to do more spatial stuff and more maps, and then Automating GIS is perfect for that. And it's part of the Geography Master's program, but it's open to anyone who wants to participate. So I hope that you will, if you're a geographer or interested in the spatial stuff and enjoy this course, then you're welcome to join us in the next period.
Okay, great, thanks. And yeah, just the important thing to note at the moment is that there are 2 separate course codes for this course. There's one for geography students. So the Geog 329-1 is for the first part of the Automating GIS processes, which is the same as the Geo-Python course. There's sort of ugly explanation for why we still have 2 separate course codes, but essentially we meet in the same place at the same time and do the same exercises, but there's one course code for the geography students and a separate course code for the geology students. At least that's the way it's intended for things to work. So you shouldn't sign up for both, for instance. You should choose one or the other. And then in the second period, there is a separate course code for the second half of the AutoGIS course. let's see. So there's also this Introduction to Quantitative Geology course. It has its own separate course code as well. It's less confusing perhaps because the course title is also different, so it might be somewhat intuitive. The Geo-Python course is offered as a bachelor's level course to the geology students, and the Introduction to Quantitative Geology is a master's program course. However, I'm often happy to have bachelor students join if they're motivated to take that course. And essentially what we cover in the Introduction to Quantitative Geology is a little bit of geostatistics, and then some applications of simple numerical models that are written in Python to explore geochronological data. So in this particular case, we introduce a set of different kinds of equations that you can solve using Python and apply them to explore geochronological data, just because it's a nice common application where many of the equations can be applied. And so we'll do things like calculate goodness of fits of ages that we can calculate with a numerical model and how they compare to ages measured from some field area, for example. And this is a 5-credit point course. So if you have questions about this, you're more than welcome to contact me for additional information, and I'd be happy to share more. Or you can go to the course page and see what was covered in the previous version of the course. But now we're going to move to the next step, which is to get a little bit of information about who you are. And we're going to do this by doing a little online poll. So if you take your web browser and direct yourself to this link here, geopython.github.io/poll, you will see a question there, and I will just jump over here. Maybe we can put this link in the chat so that's easy to find. I'll jump here to the web browser for a second, and let's see. Maybe I can make this question visible. So if you go to the poll page, Håvard has kindly put the link to the poll into chat. You can go there and just tell us to start, which course are you enrolled in? Okay, so it looks like we've got a fairly strong representation of the AutoGIS students today. I'm not totally surprised. I know a number of the geology students are in the field for field courses, which is kind of what happens this time of year. But we do have some joining us from Aalto, so welcome, and some with this enrolled sort of question mark status, which I suppose is possibly related to CISU issues, or I do know there are also some who are just joining. If you're having issues with getting enrolled in the course and you would like to be, you can perhaps let us know either in the chat, or we will introduce this Slack system where we can do some conversations in the sort of online chat environment that stays alive between classes, not just in the Zoom chat. So you could also ask questions there. We'll get to that. But if you're having problems with enrollment, let us know. We can't solve problems with CISU necessarily, but we can at least raise the issue to those who can help. But yeah, welcome everyone to the course. And maybe, Håvard, can we jump to the next question? Are you able to switch it? So what we'll do here is now switch to another question about how much programming experience do you have? This is always an interesting one. All right. So as you can see here from the distribution of the people that we have present today, at least, the winners are those who have no programming experience at all. And that's great because the course is really designed to start from the basics with no assumption about having any previous programming experience. And some of you may have had a little bit of experience, or some may even be able to write their own programs, perhaps in different programming languages, or maybe you learned to program and it's been several years since you've used it and you want to kind of refresher. But that's great. I mean, really what we're looking for, honestly, in the distribution of students that we have here in the course is that we have some who have no experience and some who have a bit of experience. And we'll get to this when we talk about the exercises, but we're going to be pairing you up with others in the course to work on the exercises. And we're trying to find pairs where we put someone who's brand new with someone who's already got a little bit of experience so that you can both learn from one another. So this is great. This is nice to see that we have this kind of distribution. Now, let's maybe jump to our next get to know you question. And that one is about which programming languages you have used previously. So again, not a huge amount of surprise here, perhaps. There are some who've used Python before. That's great. I think you'll still hopefully learn some things from this course, even if you have previously used Python. If you used R, you'll probably understand some of the programming concepts that we will include in the course, but maybe would benefit from, of course, knowing the Python syntax. But also there are some who've done Java or JavaScript programming, a bit of C, C++, and C# programming. Some have used MATLAB and some have used other languages. But of course, there's also people who have not done any programming whatsoever previously, which is perfectly fine. So it's always nice to see, sort of each year that goes by, I sort of shed a tear for the fact that no one programs in Fortran anymore, even though I'm a sort of gradually becoming one of these sort of antiques who still knows how to program in Fortran. I don't know how many years it's been since anyone has actually clicked and indicated they've programmed in Fortran in the past. But yeah, what you can see basically is that the languages that are popular now, the ones that are really kind of actively being used in data science and in other fields, are the ones that are really strongly represented here. So that's great. And we have one last question for getting to know you. And for this question, you're able to fill in your ideas of the kind of expectations, the things you would like to learn from this course. Again, it's nice for us just to know, what are you expecting, or what would you like to come away with? And I believe if you agree with some of the existing responses, you can click and sort of give your vote to those as well. So if someone's already written something that you like, you can click on their responses. And yeah, these are looking quite good, and I suppose somewhat like what we would expect. Programming with the GIS twist is the current leader. Of course, that's not a surprise given the strong representation of the auto GIS students in the course at the moment, I would very much expect you to be interested in how you can learn programming and apply it to GIS. And that's something that we will really introduce more in the second period, in the second half of the AutoGIS course. The GIS twist will be introduced more strongly, but we're going to focus in the first period really on the kind of fundamental programming concepts. However, things will be applied to data sets that are of mutual interest, hopefully, to both the geography and geology students. And so that twist may be stronger in period 2, but we'll try to keep it interesting for you, of course. And yeah, knowing how to use Python to make maps, I think that's something, when you look at the ways in which you can produce maps, of course, you can go and use QGIS or ArcGIS to make maps in a kind of very mouse-heavy point and click type way. And that works very well, and you have a lot of control over things. But you can also learn to automate things and to make maps using Python so that you can reproduce several versions of maps or different types of the same kinds of maps, same style with different data and whatever. So that's some of the stuff that I think can be quite appealing about learning how to use Python in that sense. But yeah, learning the basics of programming in Python as a language, that's one of our core goals. So that's great to see here. More stuff about learning Python and GIS, programming and some GIS stuff, basics of Geo-Python. As you can see, there's quite a bit here, and all of it looks relatively to basically be within the scope of what we're doing. So to plot charts without Excel, we will do that. So I'm with you on that battle. Anything that's not R, well, I suppose it's Python, so it's not R. But yeah, this is great. So hopefully you have some sense as well. Now we do of who you are. Hopefully you also have a sense of who else is in the class in terms of what their interests are. You probably know some of the people that are in the participants list, but of course, not being in the same classroom, it's not quite the same as things would normally operate. But basically, yeah, now we have some sense of who you are, and thanks very much for the responses. And I think what I'll do is jump back here now to our slides and continue from this point. So what we want to do in this part of the course is basically to accomplish 3 things. And by this part of the course, what I mean is the Geo-Python course, or the first half of the AutoGIS course. So we're going to introduce the Python programming language. That's hopefully clear in the title. Develop some basic programming skills. So again, we don't assume that you have any programming experience at this point. And part of the way in which we try to introduce things is not just to say, here's Python and here's how you type this in to do some operation, but rather to talk about developing these skills, how to think a little bit like a programmer, how to approach solving a problem in the way that a programmer would solve it. And then to discuss some essential quote unquote good programming practices needed by young scientists. And young, I suppose, probably should be replaced by junior scientists, not necessarily young in age, but young in terms of experience, perhaps. And these good programming practices are the things that will allow you to embrace ideas like open science, to make your results more easily reproducible and shareable with larger audiences. These are things that we try to embed throughout the course that will hopefully also produce some secondary benefits to you while you're learning Python. Now, for a bit of motivation, I'm going to jump over here to the course webpage. I can go through my tabs to our lesson 1, the first little section here. So if you want to follow along on the course page, you're welcome to, or you can just simply tune in here. But the motivation for the course that we want to start with is a simple one. So we have these different ideas about introducing you to programming in Python and some of the other things that we think would be useful for you to learn along the way. So writing programs that are easy to understand and share. You can write a Python program many different ways to do the same thing, but it's some ways that things are written that are easy to understand and other ways that might be much more cumbersome. We also want to introduce keeping a log of the changes you make to your program. So we'll be using software called Git and a website called GitHub, where essentially you can keep track of the changes you make to your programs. And so you can always go back in time if you break something. or you can see what was changed when. We're also going to create programs that ensure that your science is reproducible. So one of the ideas that's important, for instance, with open science is that you produce a result and someone says, hey, how did you get that plot? And you can say, well, here, take my Python code and make it yourself. You can see exactly how I did it. And then finally, producing some effective data visualizations, simple, effective data visualizations to make your results accessible and easy to understand. And that's kind of where this motivation starts here. So if we consider the idea of effective data visualization, this is something we get to toward the end of the course after we know a bit of the basics of Python. And the reason for this, or the motivation for this, is quite simple. This is what data looks like. So here we have I think this is like the first 30 lines of some global temperature data file. And if you look at it, of course, this is only the top 30 lines. It continues for maybe another 5,000 lines after this. If you look at it, I don't find this to be particularly inspiring. I'm not learning very much about the data set from looking at this file in this particular view. And this, of course, naturally is why we want to visualize the data, because this just isn't very interesting like this. It doesn't tell you the story. It doesn't convey what might be really important information about things like climate change that could be contained within this data set. So one of the options we could consider is to take something like this data file, load it into some software to create a plot, and make an XY plot of the temperature data. In this case, we're showing temperature anomalies over time. So this is a kind of difference between the temperature in some year compared to a long-term average. And what you can see from a plot like this already is much more than you could see previously. Now we can see that there was a period of time prior to the 1940s where temperatures were generally below average. Then there's a little blip in the 40s, and then temperatures kind of hover around average until about 1980, where they then start to increase significantly toward the present day. What we can see in this is very accessible. It's easy to digest. This is the same data represented in a different way, and visualizing things like this conveys a message that allows us to talk about topics like the possible changes in climate that we're observing in this climate data set. So obviously this is much better. What's lacking here, however, is a geographical context. So if we're looking at global temperature data, global mean temperatures, this is perfectly fine, but maybe we want to say, well, how has the temperature changed in Finland? Or how has the temperature changed in some other part of the world that we might be interested in? And for that, we can consider displaying the same data in a different format. So here is an example of plotting basically the same kind of data, but now on a map. So these are global temperature anomalies from the U.S. National Oceanic and Atmospheric Administration website. And what we see here is the departure from the average temperature for the month of January in 2020. And this past January, we happened to have a decent winter, but last year, if you can remember, for those of you who were here in Finland, it was a pretty poor winter, and it was actually one of the warmest Januaries on record. And you can see in this kind of representation of our data exactly that. Temperatures here that are something like 5 degrees or more above the average temperature in much of the northern part of Europe and Asia. So this is also something that allows us to understand more about our data set. Now we have a spatial context that we didn't have before. That's quite interesting. But there's one thing we've lost in this spatial context, and that is time. We have a time sort of slice that's shown in the map here, but we've lost our connection to how these temperature anomalies have been changing over time. Maybe this January is like, well, it's, it happened to be warmer than normal one year, but on average, it's not actually any warmer in January for the past 30 years. That's not really true, but you get the idea. We've lost the time context. So in order to make a step where we try to visualize our data in what's kind of a really, I don't know if I would say revolutionary, but a very interesting and highly impactful way, we can consider some of these unique visualizations that have been produced by people using Python. So here are a couple examples. These are put together by a guy named Antti Lipponen, who is working, I believe, for the Finnish Meteorological Institute. He's pretty into data visualization. So if you go and you visit the links that are here, for instance, this is to, I don't know, Flickr or something where these images are stored. You'll see he's got a whole bunch of different kinds of climate visualizations there that are all created with Python. We'll just show you one or two just because they're pretty neat. And what they do is they combine this idea of a spatial context with a change in time and allow you to see things like how temperatures have been changing globally and over time. So this first example is what I think he called like a pill packet plot. I don't know if that's like the kind of official name, but I think I can make this full screen and hopefully not lose anything. What you can see is there's different countries that are here, and then we have these anomalies in temperature plus to minus 2 degrees C. So again, this is showing deviation from the normal value and from 1880 onward. As I hit play, you'll see these different pills kind of getting bigger and smaller, changing colors and whatever. And already just from looking at the colors, you can see some years are warmer than others. There are different areas that are having different effects of the temperature in different times. But as things go forward, what you start to see overall is a lot more orange and a lot more red. We saw this already in the XY plot we looked at, where the temperatures have been increasing over time, and we had no spatial context in that, but we have seen clearly that the temperatures are increasing over time from about the 1980s going forward in terms of the temperature anomalies. You can see it here very clearly with both a spatial and a time context in this kind of visualization. So if you're curious, you can go back onto the course webpage and watch that again. I'll show you another one here just because this was an animation or a style of animation that, I don't know, did it go viral? It was popular on Twitter for a little while and shared quite broadly on a number of different social media platforms. Again, showing this idea of temperature anomalies over time. Now you have a sort of almost like a wheel with different spokes, and the spokes correspond to different countries in North America, South America, Africa, Oceania, Asia, and Europe. So each country has its own little spoke, and the distance from the center of the circle corresponds to the temperature anomaly. So if you're right on this 0 circle, it means your temperature is about average. Of course, if you go further away from the middle, it means temperatures are getting warmer. And I believe this one actually includes a forecast for how temperatures would be expected to increase. So again, here we have a nice way to look at both space and time and how temperatures are changing. You'll see very similar trends in the sense that as we move toward the present day, there's a lot more orange and red that is coming onto the plot. And then as we project things forward in the future, this is based on predictions from climate models. Things don't look very good. And I think this is sort of deliberately done in the style of this presentation to leave the axis range as it is to show the anomalies today, and then to emphasize how much warmer it's forecast to be in many parts of the world as a result of the ongoing changes to global climate. So those are just a couple examples to motivate you in terms of why you might like to learn something about programming in Python and data visualization, because essentially we can unlock from this text file that if we scroll back up to the top here, what looks like a somewhat uninspiring text file, we can take the data that's there and process it in Python, plot it, and produce things like some of the plots that are shown here that convey a great deal of information in a simple way so that right away you can understand what is shown in the data. We won't go as far as producing plots that are as complex as this one, but we will make our own little temperature anomaly plots toward the end of the course. And if you are so inspired, I think you can actually find the source code for making this same style of plot online, and you might be able to then even try to duplicate this result for your own enjoyment. So that's a little bit of motivation. And I think now I'm going to continue with just a bit of introductory general material about programming languages, computers, very basic introduction to computing. And when we finish this, then we'll take a little break and we'll continue on with the second part of the lesson after that. But for the moment, I'm going to jump back to the slides here. And again, if there are any questions, you're welcome to post them in the Zoom chat for now. But before we can go into talking about Python programming, because we assume that you don't have any background in programming, we need to talk a little bit about computing and a little bit about some of the essential terminology to understand computer programs. So in this short lecture, we're going to talk a little bit about basic programming practices and computing practices. What is a computer and a programming language? And then lastly, what are the parts of a computer program? Now, to further the motivation part, you've already seen the nice visualizations that you could potentially make, but learning to program is something that is, in my view, it's a basic skill that is something you should learn as a student at the university now, as a science student. I sort of see this as a fundamental skill at this point. And the things that are important to note here is, like, we recognize you aren't computer scientists. I'm not a computer scientist. Håvard's not a computer scientist. And part of the reason why we've created this course is because we don't necessarily think like computer scientists either. Many of us are motivated by the data, and we want to understand the data sets that we're working with, not necessarily the intricate details of how the computer represents data in memory, or how data is transferred between the processor and some place in which it's manipulated. We perhaps are less interested in the kind of computer's architecture and more about what can we do with a programming language. And that's why we've put this particular Geo-Python spin on things, is to focus more on those things and to take small steps together to learn the basics of programming, and really starting assuming that you don't know anything about how to program. And yeah, I think it is something you really need to know. Part of the reason is that both geology and geography are becoming increasingly quantitative, and computing is becoming more and more a part of those sciences as time goes forward. Of course, we still need to make our basic observations. We still need to learn these skills that are taught in many of the courses in bachelor's and master's programs. But the quantitative part, in terms of what the researchers are doing, is something that's growing more and more. And learning these basic programming skills will allow you to be a better scientist and be more actively involved in shaping what's happening within your area of interest. So to understand nice landscapes like this is a field photo from Nepal, in the Himalaya in Nepal. And a lot of what people are doing to understand landscapes like this today is using computer models to simulate how this landscape is formed over long periods of time, because it takes, some cases, tens of millions of years to form mountains like the ones that are in the photo here. Another reason that you might be interested in learning to program is that many of the existing software packages that you might already have learned how to use have Python interfaces and have ways in which you can extend what the program can do using Python. So for example, ArcGIS, QGIS, they both have built-in Python interpreters where you can integrate your little Python programs to the software to allow it to do things that it can't do out of the box. And that's pretty cool. I mean, I think the ways that you can potentially extend software, even with a short little Python program, make it much more powerful than it might be by itself. So of course, here, a quantitative geoscientist is better than the average geoscientist. So here's an example then of QGIS. So some of you may have used QGIS previously. And what you'll see here is the Python console that you could open within QGIS, and ways in which you can interact with the layers of data that have been loaded into the visualization here. So this is a nice way to extend the software. The last point for why I think learning to program is something that should appeal to you is it's actually pretty fun. It might not feel like it every time, and I can promise you there will be parts in the course where you may be questioning the fun aspect of learning to program, but it is actually an enjoyable task to think about how am I going to take some complex problem and break it down into smaller pieces that I can write little codes to solve. How do I come up with a strategy for taking this big problem and making it simpler and into little pieces that are easy to test and to basically put together to be able to solve a much more complex problem. And this is fun. It's actually now taught to kids even at the primary school level because they think, again, learning Python is a fundamental thing, or learning some kind of programming language is a fundamental skill. And of course, there are many ways in which they can make this fun even for the kids to solve these basic logic problems. And how do you instruct some little mouse to go find the cheese or whatever? Those are things that kids are naturally interested in learning. And this can be, I think, a very enjoyable experience if you're open to it. As a scientist, there's a number of ways in which programming can make you a better scientist as well. So this is the scientific method. Probably you've seen some form of this in the past, which is basically the way science is supposed to work. So you define some question, get a little bit of information about what the question is, come up with a hypothesis, et cetera, et cetera. And all of these things can be improved, or many of them can be improved rather, by learning to program. So gathering information, for example, and resources, making observations, this can certainly be improved by programming. If you design some little Python program to pull information off the web and collect information, for instance, on social media or other sources where you have just massive volumes of data you wouldn't want to try to process by hand, a Python script, for instance, could be processing and pulling in information that has certain keywords that you want to sort of investigate further. You can also improve your ability to perform experiments and collect data. Now, of course, part of that data collection could be similar to the gathering information, but performing experiments, you might write Python programs that actually do some calculations for you to conduct some kind of numerical experiment. This also could link to the sort of analyzing your data. If you have some script to take large tables of data, read them in and process them, that's something you can definitely do in Python. And with the interpretation as well. Interpreting your data is something that's challenging in general, but nice visualizations and things like that can make it much easier to understand the data that you're looking at. The good programming practices that were mentioned earlier about these ideas we want to help you, embrace things like open science. Learning these good practices can help us do things like make sure that whatever experiments we're doing can be done in a reproducible manner. If you have a little Python code that you can hand to someone that says, yes, you can reproduce my results, here you go, it is a very strong way to stand behind what you've done. And that's one thing that I think is a valuable contribution from learning how to program with some of these things in mind. Additionally, retesting is something that you may want to have other people do just to make sure that your results are robust. And again, you can say, here's my Python code and go and see if you get the same results I did. So these are all, there's many things where we're learning how programming itself can help, but these good programming practices can help as well. All right, so now we have another poll question for you. So I'll let you think for just a moment here. The question is, what is a computer? And again, you can go to the link that's in chat, for instance, or you can click on the link that's here on the slide. It'll take you to the same place. Maybe you need to just check that the question is up. I don't know whether Hovard has been. Yes, he's on top of it. So thanks for that. And I'll just copy the link here one more time just to put it down here further toward the bottom. Oops. Didn't copy for some reason. In case you're not finding it, the link is now at the bottom of the chat. But yeah, you can provide here some idea of what you think a computer is. And again, I think you can click and vote on the options that you think fit the definition best. So still have a few options being added to the list here, but I think there are a few leaders that are standing out. So one of them is wise machine, another is a code processing machine, aka a fancy calculator. And yeah, there are aspects to this. I mean, a wise machine, I suppose it depends a little bit on your definition of what wise is, because wisdom to me would suggest the computer has learned something over a long period of time, and it has an ability to call upon existing and past knowledge to make decisions. And there are parts of that that are, for instance, part of what artificial intelligence would include is this kind of idea of learned experiences. The computer itself, maybe I wouldn't want to necessarily call wise, but I like the sort of idea that's conveyed here. The fancy calculator, in a sense, yeah. I mean, we'll talk in just a moment about what makes a computer different from a calculator, but in some sense, it is a fancy calculator. What the processor is doing is basic math operations. And in some ways, then, that is pretty much the same thing a calculator is doing. A system to perform calculations, yeah, I think that's definitely part of what the computer can do, a device that analyzes and processes information into actions. Again, it can do those things. The processor is part of a computer. I think the computer itself might be a bit bigger than that. But yeah, there's a couple of references here to handling binary information, and that's also something that ultimately is what's happening inside the processor of the computer. Is it's processing code that is in binary. It's ones and zeros that determine the actions of the computer. So many of the pieces are here, and so I'm happy to see that, of course. If we ask a computer scientist what a computer is, this is about the simplest diagram you can come up with. And what it looks like is basically there's a box here that contains a central processing unit, or CPU, some memory in which the CPU is able to store information and retrieve information from a bank of memory. There may be secondary memory. In this case, could be something like a hard disk or someplace where information can be written to be stored. And then we have an input device and an output device. So we might have a mouse and keyboard and a screen that could be our output device, or a printer, or whatever you want. But basically what it is a machine that stores and manipulates information under the control of a changeable program. Now we can break this definition down a little bit. So manipulation of information means that you have something coming in, something happens inside the processor, and the output could be the same, but hopefully the output that goes out is something that is new and perhaps more usable than the input. So if the input was a data file of climate data, maybe the output would be a plot that makes this data into a form that is new and more useful for our understanding as humans. The changeable program piece is a sort of essential element of what a computer is. And that's what distinguishes it, for instance, from a calculator, is the fact that the program can be modified to do different things. So the program that is running Many of the operations that are happening on my computer would be Mac OS, for instance. You might be running on a Windows computer where the operating system, there are many different programs that are part of the operating system, but all of those change, and they happen sometimes at inopportune times when you want to give a presentation and your computer says, oh no, you need to install this critical security update and it's going to sort of reboot right now. This changeable program happens all the time with the software we're using. It gets updated, it gets modified. If you buy a sort of basic calculator, it is hard coded to do a certain set of operations and its program is not changeable. And that's what makes it different from a computer. So in a sense, a computer is a fancy calculator because its program can be changed. If we consider fanciness to be whether or not you can change the program, but for a basic calculator, it would not be considered to be a computer. But for instance, a smartphone would definitely be fitting the description of a computer here. The smartphone has a processor, it has memory, it has a screen where you can see output. You can smudge your fingers across the screen to input things. And it may even have some sort of secondary memory. Most probably it does, where you can store things like photos that you take with the camera. They get stored in the memory, and when you turn the phone off, it's not like those photos go away. So basically, a smartphone would qualify as a computer. What are they good at? Well, there's a number of things computers are good at, and I'm sure you are familiar with some of them. They excel at well-defined, clear tasks. So if you tell the computer to add the number 2 plus 2 and return the answer, this is how you would do that in Python. You could print 2 plus 2, and what you will see very quickly is the answer of 4. That's because the computer doesn't really have any uncertainty in terms of what's going to happen here. This is a number, this is a number, and this is a mathematical operator, and the computer understands all of that, and then the print statement says, display the result. Nothing confusing about that. Computers are also good at data storage or data manipulation. They can be. So, many of the fundamental internet services of today, these Google services and all the kind of massive web services that we use rely on efficient and effective data storage and manipulation. Computers are also good at repetitive calculations. So, the same thing that happens in the program over and over again. Once the program exists, the computer has no problem to do it many times over, provided that you don't somehow overheat the processor or something like that. There's no limitation to repeating calculations. And processing data or instructions, that's essentially what a program is going to tell it to do, is to do something in the form of some instructions that the computer understands. So again, this is our Python prompt and how we would print 2 plus 2 in Python. But computers aren't good at everything. So abstract or poorly defined tasks are things computers are not very good at. So if you were to tell the computer, calculate pi, you might think, oh, that should be easy. Computer knows how to do that. But if you just tell the computer, calculate pi, and you don't tell it how to do this calculation, the computer's going to struggle. It needs to have a clear description of how it should solve this problem. And of course, computers are very good at doing these calculations. This is the first 1,000 digits of pi. I think I saw something in the news about some obscene number of digits pi has been solved to now. Number of decimal places will think on the order of several billion, but I don't know. But yeah, kind of ridiculous. And as long as we define what to do, calculating pi, for instance, is no problem for a computer at all. And another thing that you could think of as something computers aren't good at are tasks that are simply not computable. So this is a rendering of what the Lumi supercomputer cluster will look like. This is going to be installed and has started to be installed in Kajaani. It is a European Union level supercomputing resource. And I think it's going to be the biggest supercomputer in Europe when it becomes operational. It's got something like 200,000 processor cores. So if you figure your typical laptop has one, it's got a lot of computing power. In fact, the little graphic on the website for the Lumi supercomputer says it's got the same computing power as 1.5 million modern laptops. So, and they, because They want to sort of make the point, show you here a nice little rendering of Mount Everest, and that if you stacked 1.5 million laptops on top of one another, they would be 23 kilometers high, something silly like that. But even this supercomputing resource is, one of the most powerful supercomputers in the world, cannot solve tasks that are not computable. If you were to say, computer, where are my car keys? Very probably this computer, even if it uses all of its processors, isn't going to be able to tell you where your car keys are unless you provide some additional information. You can also come up with things on massive resources like this that simply cannot be solved. So if we wanted to calculate the temperature in the atmosphere at 1 meter resolution globally, the size of that calculation is so big that the computer simply cannot handle that much data at once. The size of the problem is too big to be solvable. So there are things where there are practical limitations that we should be aware of. All right, so a few things now about programs and programming languages. First off, the question, what is a program? And I won't make you go to the poll for this one, but instead, I'll show you a couple examples here and then we'll give a basic definition. So this is an old school Fortran punch card. This does predate me, so I'm not this old of a Fortran programmer. This is from like the 1960s and 70s. But this is what a program looked like in Fortran back in the day of punch cards. And essentially, when you wrote a program, you had a big stack of the punch cards. Each one of these numbered positions in here would represent some operation the computer was going to do. And if there was something punched out, you would feed the punch cards into the computer and it would carry out the calculation that you've instructed it to do based on what you've punched out from this punch card. Fortunately, we don't have to do that anymore. And instead, we can deal with things like this. So again, this is a little example of a Python code. What it does isn't really important, but of course, this is much easier for you to maybe start to interact with code like this compared to a bunch of 1 through 10s that are punched out of a cardboard or paper card. So what the program is itself is this detailed list of step-by-step instructions that tell the computer exactly what to do. Computers generally don't like uncertainty about how to proceed. So a program like this one here says, take the value here for some data variable. So this is a variable that's got some data in it, doesn't really matter what. Take a selection of the values out of this data variable and store that as another value called misbit. There's no uncertainty for the computer about what to do here. Another thing about the program, of course, as we've mentioned, is you can change it. And when you change the program, it will change what the computer has to do when it's executed. And the name software is just another name for a program. So you'll sometimes see these used interchangeably. Software normally sounds more important, but if you want to feel important about what you're doing, you could say, oh, I'm writing Python software for my course. And I think people will have, I don't know, a bit more respect for no good reason whatsoever. What's a programming language? Well, this is essentially the way in which we can talk to the computer. We have spoken language. So obviously I'm speaking English now, and you're hopefully understanding at least parts of what I'm saying. If I were to do the same thing in Finnish, you would understand far less of what I'm saying, and I would be able to say far less about what I'm trying to communicate. But this is the way in which we talk to one another. A computer's programming language or a computer language is the way in which we as humans talk to the computer. So we have some things we can do. You've used Siri maybe, or Alexa, or whatever the OK Google one is, to say certain things to smart devices that could then interpret what has been said and turn the lights on or tell you what the weather's going to be or something like that. But we don't really tell the computer a whole program at this stage. And we can't just say, do some calculation to the computer and expect it to understand what we want from the computer. The programming language is basically the code of the instructions that the computer can understand and that we can hopefully understand. So we understand the instructions we're providing to the computer. The computer then, when it receives the instructions, understands what to do. And there's a couple aspects to a programming language that are important. One is that it's exact and unambiguous. So that means that when you give a certain command to the computer, it knows precisely what to do and doesn't have to go like, ooh, did you mean print or did you mean something else? That's not going to work very well. And for the programming language itself, these are just a couple terms in case you're curious. It has a precise form, that's what we call the syntax, and a precise meaning, that's called semantics. These are maybe not so important for you to remember, but just you might see syntax error come up at some point, which generally means that you've said something and the form of what you said for the Python program to do is incorrect. And Python itself is just one of many different programming languages, as we've already seen in the poll. So before we take our break, we're kind of moving toward that time in the course for today in the class. But before we take our break, we can talk a little bit about the sort of strategy for developing a program. It might seem like you just want to jump in with both feet and start writing your Python code right away when you have the task in front of you, but it's worthwhile to spend a little bit of time to think about the problem before you actually take the steps toward writing your Python code to address the problem. So we have this general strategy. This is something we won't really return to, but it's worthwhile to consider when you start working on some of the exercises. Some of these elements might help you and save time in the long run if you think them through before you start actually writing your code. The first is to kind of do an analysis of the problem. Then you can think about, okay, well, now that I understand the problem, what do I need to solve the problem? And then you can come up with some idea of how you might solve this problem before moving to the fourth step, which is basically writing the code, where you take your how you're going to solve the problem and convert it to a way in which the computer can help you and understand what you're doing. Then you can test to see if the program works, and then if necessary, you can maintain it. If you've written something you think that would be shared and usable by other people, you might want to maintain it and fix things in the future. So as an example, I was lucky enough to be born in a country that's still clinging on to the imperial Fahrenheit temperatures. So for me, I mean, each year that goes on, this kind of gets less and less true, but I still understand temperatures in Fahrenheit. I haven't lived in the US in a while, but for us, 70 degrees is a lovely temperature. 90 degrees is hot, and water freezes at 32 degrees in this intuitive temperature measurement system. The problem here, of course, is that the temperatures are normally reported in Celsius. And so if I hear a temperature in Celsius, maybe I'm going to be uncertain about what I should wear when I come to work, for instance, in the morning. So I think I need a program to solve this problem, to convert temperatures like this, or convert temperatures in Celsius into something I understand in Fahrenheit. So in our example, the first step is to analyze a problem. That's before you can solve it, you have to figure out what should be solved. In this case, I think it's pretty clear. What we need to do here is come up with a way to take a temperature in Celsius that has been, on some website, and convert it to Fahrenheit so I can understand, oh, okay, that's going to be hot. I should wear, shorts or whatever. That's the basic problem. The specifications in this case is the step where we describe exactly what this program should do. We don't have to worry about how it's going to work. It's just like what is going to go as an input, what's going to be output, and how things would work. In this case, essentially what I want to do is take a temperature in Celsius as an input, and the output should be a temperature in Fahrenheit so I can understand what clothing to wear. After that, we can talk about the design of the program. So overall, how are things going to work? How is this going to be designed? And this is often what's called a stage where you write pseudo code. And this is precise English or Finnish or whatever language you prefer to speak, but you can write down basically what you're going to do. So for instance, I could write down that first I will input my temperature in Celsius. Then the code will convert the temperature from Celsius to Fahrenheit. And finally, it will print the temperature in Fahrenheit out to the screen so I can see what the converted temperature is. If I wrote that down basically more or less as I said it, that is the pseudocode that basically outlines what the program should do. And it makes step 4 easy, because if we've done a good job with our pseudocode, all we need to do now is just convert that into the syntax in Python. So we just translate the pseudocode into Python. We've already solved the problem. The implementation becomes much easier at this point. And this is the reason I sort of show this at all in the course, is just to emphasize that, you know, if you do the thinking up front before you start messing around in Python itself, you can save yourself a lot of time, because this implementation step can be quite simple. Now, at this stage that we've written the program, we can now test it. And so what you want to do is take your Python code and basically run it to see whether it reproduces some kind of expected value. This could be considered like a test case. So a test case that we might think about is that, hey, if I put in a temperature of 0 degrees Celsius, I should get 32 Fahrenheit as my output. And so you could put those values into your program and see whether or not you get the expected value coming out. You could consider another case of maybe if you know the temperature of boiling water is 100 degrees C at sort of atmospheric pressure. And that same temperature in Fahrenheit is 212. So again, we should expect to see, if we put in our input value of 100 Celsius, that we get 212 Celsius out as the, 212 Fahrenheit rather, out as the output from the program. So that's the testing. If we're not getting those values, then there's a problem in the code, and that needs to then be debugged to figure out why is it not giving me the value that should be output. And finally, if you've written a program that is something you want to share with other people, you may then feel some obligation to maintain it and make sure that it continues to work. If there's some kind of security risk, you might want to have that in mind so you can fix things so that people can continue to safely use your program. But that's the basic idea of the development stage. Now, at this point, I'm going to skip over this little recap